Hi there, great to see you again on the online course Easy Geosteering. In this course we simplify the main geosteering topics, breaking them down into easy-to-understand concepts. We are currently in the first part of the course, Necessary Theory, and in the previous video we covered drilling and landing strategies. And today we explore the main attachments of Geological Project. Let's get started. Let's take a look at the planned trajectory from a real example. First, we can analyze the well design. This well has a conductor pipe, surface casing, intermediate, and production casing. Next, we can spot the main horizons, marker 1, 2, 3, and 4. TVDSS values for these horizons are taken from the 3D geological model of the oil field, once the planned trajectory is placed on it. Then there is a row indicating the first point of gamma-ray logging. This is relevant for MLWD engineer as it tells them when to start recording gamma-ray while drilling. For us is more important the row indicating the start of the geosteering support. In this example, we start uploading MLWD data and monitoring the situation at 2500 meters MD and inclination of 72 degrees. The start point of the geosteering support is chosen not too close to T1 in order to have enough time to adjust the trajectory in the landing section. And also not too much in advance, since geosteering in the upper section doesn't make much sense. Point number 5. Pumping equipment. For us it means we cannot change trajectory in this interval even if we need, because this equipment has to be placed in stabilized section of the well bore. Point number 6. T1, T2 and T3 positions along with the landing strategy. In this example, we need to enter the target layer within 20 meters MD and complete the landing section with inclination of 87 degrees. And the last point to note, stabilization interval M1-T1. This means that we need to reach the required inclination of 87 degrees within 20 meters MD before the top of the target. As you can see, there is a ton of critical information into this part. Analyzing it carefully is essential before providing real-time geosteering support. The next part of the geological project is oilfield geology, risk and hazards while drilling. Let's start with the limitation on DLS. In this current example, in the landing section we cannot exceed 2 degrees per 10 meters, while in the horizontal section it's even stricter, 1 degree per 10 meters. This is a pretty common scenario since the horizontal section typically has more requirements due to completion assembly. Next point, risk and hazards. In this example, we can see fragile rocks between marker 3 and 4, which could potentially lead to issues with the quality of inclination building, and we need to keep it in mind during the landing section. Point number 3, brief information about oilfield geology. The main lithology in the zone of interest is sandstone, claystone and siltstone. Here we have high compartmentalization, which means the target layer contains numerous thin sublayers with different rock matrices. On the bright side, we don't expect faults and also significant lateral changes because of high reservoir continuity. However, it's important to note that we have an oil-water contact at a specific TVDSS. And point number 4, LWD reference values. These are extremely useful for determining whether we are within the target layer or not during the drilling process. Okay, let's move on to the attachments of the geological project. The first one is the structure map. We gave the definition in video number 3, now let's take a look at some example. In this map we can observe the drilling direction and the expected behavior of the layer. The current well is planned to drill toward the southeast, and along the well path we anticipate the layer is dipping down. The strike line spacing is 4 meters, and near T1 point the predicted TVDSS of the top target is -1236. By the end of the well it's -1244, meaning the layer dips downward by 8 meters from T1 to T3. The next point, offset well positions. These are the closest offset wells and we should include them in our geosteering model. And finally, on the structure map, we might also see reservoir limits, faults, and license areas designated for a specific customer. These elements are important to ensure compliance with both operational and regulatory constraints. The next attachment are geological cross-sections with lithology, porosity, and permeability. From this picture, we can observe the layer behavior and how the reservoir properties change along the trajectory. Here we can notice that the layer is deepened down along the horizontal part and has lots of sublayers with varying permeability and porosity. Also, we can observe an approximate visual of the lateral changes happening in the formation. Point number 3 is the plane trajectory itself, including the positions of T1, T2, and T3 points. It's also convenient to analyze the oil-water contact position relatively to the well. And finally, sometimes you may find details about the completion method. While this specific example doesn't include it, in other cases you might see frac ports along the trajectory. And now let's talk about the correlation scheme. This shows the logging curves from the available offset wells along with the horizons and fluid contacts. So what can we do with the correlation scheme? We can use it to predict the top target TVDSS for the current well by assuming equal thicknesses of the upper layers across all wells. It also helps evaluate variations across different wells, giving an idea of the extent of lateral changes. What do you think? In this example, are there any lateral changes between the offset wells? At first glance, this section looks pretty continuous, but if we take a closer look, we can spot, for example, slight thickness changes of the layer M2 and M3 between the first and second wells, as well as some differences below the bottom of the target. Strictly speaking, lateral changes between the wells always take place to some extent. Alright, we have covered the main attachment for Geological Project. Hope you liked this video. Remember, you can boost your practical skills with the private lessons. In StarSteer we utilize modern drilling simulators to provide you with an immersive experience of a real geosteering engineer. So stay tuned and give this video a thumbs up. In the next lesson we will explore the geosteering job cycle. See you then. Bye bye.